Hi, Calc. Good morning. Welcome, everybody. I know we're still missing a few, but I'm hoping through our check-in question we could catch some. I don't remember. I feel like Okay, what's a cute animal for you? By the way, don't limit yourself. Some people think snakes are cute. I've been learning a bunch of new animals through this discussion. So, what's a cute animal just in general? Maybe it could be something we don't know yet, or like an animal that not many of us know. All right, let's see. So in general, okay, dog always, monkey. Yes, monkeys are cute. Cows, oh my gosh, somebody finally else thinks cows are cute. I love cows, especially when they're uniquely colored. Okay, golden retriever mixed with German shepherd, cats, yes. Panda or giraffe. Oh my gosh, I never heard of a giraffe being cute. So that's a new perspective. A leafy sea dragon? I haven't heard of that. So that's something I'm gonna have to look up. And sables too. Puppies. Awesome. I'm gonna have to look up what in the world is a leafy sea dragon. It's funny because I was looking up animals because people have been mentioning these new animals I've never heard of, and I've forgotten them, like most of them. I hope I remember what this is. Leafy sea dragon. What in the world? Western hognose snakes. Okay, so that's a leafy sea dragon. I don't know if y'all are looking it up, but on my phone, this looks like yeah, it kind of reminds me of a seahorse. Okay. I wonder if they're petable. All right, and then we have okay, I don't know what a sable is. Yes, those are cute. Oh my goodness. This is a new cute animal now I'm gonna share and probably look at. That's a sable. Hecka cute. It looks like a bear mixed with a squirrel. Or it looks like a fox. Sorry. So that I love that one. Thank you for sharing. Birdies, rainbow parents, parrots. And then the last one I'm gonna look up that's new to me. So I'm gonna for sure remember the sable. But let's see. Western hognose snake. So Western hognose snake. That's what this looks like. I mean, it's a thick snake. Sorry for those who have snake fear. Some people actually get really like, ooh, with snakes. All right. Thank you for all these new animals. There was another one that I forget. Like I was like I put like my picture of myself riding a water bear or something. Those look very like I looked it up. Some people think they look cute, but I don't know. Someone said it looked like a tapeworm, and then they lost the cuteness after that. All right. Let me go ahead and sorry, I got distracted because I'm looking up cute stuff. All right, so I just checking in who we just got and who I'm missing. All right, so this is who I'm missing. Oh, okay. I'm missing Kaylin with a C. Kaylin with a C. And that's it. I am missing Grecia, but her absence is excused. So I'm just missing Kaylin with a C. So if you're friends with Kaylin, if you could send him a text. Other than that, thank you all for sharing. Um, Cute animals. Okay, we got a sphinx and then a baby lion. Oh, I also think churls are cute, but okay. All right, y'all, let's go on to our agenda today. So it's gonna be our last class before we hit break. Um, we have asynchronous number 11 that's due tonight, and that one is you trying to do the formal definition of the derivative. So I'm not exactly sure who got started on that, but That's the thing, like, for those of you who were in pre-calc last year, that's the thing we kind of ended our unit with, like, actually using the formal definition to calculate the derivative. But last year, we didn't say derivative, we said instantaneous rate of change. But now that you're in AP Calc, we do call it the derivative because it has other applications and other extensions to it. All right. So today we just had our attendance and check-in. We're going to be doing interactive notes. What I mean by interactive notes is usually it's like I try to pause and have participation portions within, and I do give credit for those participation portions. So for today's note, we're going to have a Google Doc participation in the middle-ish or beginning-ish, and then at the end we have an exit ticket. And just so y'all know, the last assignment before you hit your break will be async number 12. That's going to be due on Sunday. And after that, you'll have nothing for the break that's coming up after. And yes, you have a whole week off next week, a whole week. Wait a sec. Hold on. Give me a sec. Nope. Okay. Sorry. I thought I was missing someone else. All right. So, first off, make sure you have your notes ready, whether that is that you're doing electronic notes or if you're doing written notes, however it is that you're taking notes, just have those out and ready. I will start with a recap of what we did last time, and then I'll let you know when we should start writing things down. Are you gonna give us homework over break? No, that's up to you all if you want to. Like, for example, if you log into your College Board, there's additional practice for like AP Calculus exam style questions. That's up to you if y'all want to do that. You can also like go on Khan Academy. They have an AP Calculus, like a series where you can look through the videos. Because again, given this modular system, it's gonna be hard to hit all the stuff we need to cover for the AP exam. So you definitely want to try to self study, but that's up to you. I'm not going to assign anything over the break. Yeah, I used to do that, but that was when we had classes in session. But it's okay. Don't worry about that. Yay, we got welcome Kaylin. We got Kaylin. Kaylin with a C. Let me go ahead and fix the attendance. All right. Cool. So let's go ahead and have our notes ready. And this right here is a recap. So we're not writing this down. This is just me recapping what we did the other day. So the other day, we talked about what the instantaneous rate of change was. How does that relate to what is a derivative? And our learning target from last time was I can find the instantaneous rate of change of a traveling object and make connections to its representation on a graph. And we're basically looking at how the secant line was changing and getting more and more steep as you were getting a better instantaneous rate of change approximation. So that was what we did last time. You don't have to write this down because you already have it down. And this was from last time, so don't write this down. So where we left off in the function is we made this last approximation. Like this was like, a point that was really, really close to the point of interest. So we were interested in finding out what is the instantaneous rate of change of this ball. I believe this was a ball being thrown at exactly x equals 2 seconds. And what we were doing was moving this green point, that second point, closer and closer to get a good estimate. And where we landed on with our estimation method was negative 7.9 meters per second. And I remembered to include the units there. Super important because we're talking about a rate, the instantaneous rate of change. So that's why it's important to add your units. Similar to velocity. Velocity is a rate, speed is a rate. So that's why I include the units as important. All right, so that was from last time. So again, you're not writing this part down. That's just a little recap. Okay, now this is the part you want to write down. So we didn't get to hit this. I know the exit ticket asked you some questions about the tangent line, and many of you actually remembered some stuff, or some of you actually went to the slides to look it up, and that's fine. So the tangent line, like how does that secant line and our approximation relate? So basically, once our point is on top of the point that we want using limits, right? We had the formal definition of the derivative with limits. We get what we call the tangent line. Visually, that looks like a line that's touching the graph at exactly one point, and it's exactly tangent to it. Tangent means exactly touching. and it's not touching more than once. It's just touching at exactly that one point. So if you, it looks like it's intersecting more than that, but if you were to zoom in on Desmos, you'll see it's not. It's only at exactly one point that this line is touching that graph, and at that point is at x equals 2. So here's some stuff to write down. The tangent line is the line that touches the point of interest at exactly one spot, one location. So this is what you want to write down, so this part. The next thing that's important to know is the slope of the tangent line is the derivative. When I'm saying derivative, that's the same thing as me saying it's the instantaneous rate of change. The slope of this line is the instantaneous rate of change. And just so for some background, the word tangent comes from the Latin tangere or tangere, which means to touch. So like just as a background on where that word came from. And let me also write right here that the slope of this line is the instantaneous rate of change, or the derivative. And remember, we had that definition of what was the instantaneous rate of change. It's that big one where it says the limit. Let me write it down. The limit as h approaches 0, and this was from our last lesson, of f of x plus h minus f of x, that's your change in y, all over the distance between the 2 points, which we said was h. And when we're moving those 2 points closer together, that's why we have the limit in the front. So the slope of this line is the instantaneous rate of change. This is how you calculate the slope of that line. And again, we call this the derivative in calculus. So that's just definitely get this down. Let me leave this up for like a few more seconds. You want to get the visual and the definition. It's important to get both of those. All right, there's something in the chat. Did you want us to get this graph in the notes too? If it helps you, yes. I personally am like visual and verbal. No, for me, I'm not a verbal learner. That means if I hear something, if I don't write it down or write it, if I don't write it down or draw the representation of it, it's not going to stick. So it depends. So if you're a visual learner, yes. If you're not and you work better with just word description, up to you. I'm not requiring you to get the graph done, but it is a good idea. And then it's on the slides too. If y'all want to go back and check them out, it's on my Google Classroom. Y'all have access to the slides. All right, let me go ahead and clear this up. So I'm just going to clear the little notes I made here so I can move on to the next slide. All right, so the homework that's due today looks like this. So the homework that's due today, you're being asked to calculate derivatives, aka instantaneous rates of change, using the formal definition for instantaneous rate of change. Now, this was that definition, and this is actually a video that I used for pre-calculus. Maybe some of you remember it. But in the homework, I kind of link up this video, ask you to watch about 10 minutes, copy down some notes, and I ask you to try one problem. So it's not a bad assignment at all. You're just asked to copy notes and do one problem like this. But as you can see, to calculate the derivative is very lengthy. Look at the scratch work you have to do and look at all the steps. And you also have to be careful in your steps, because if you mess up a sign, you mess up the whole problem. So ultimately for this particular problem, we're trying to find the derivative of this type of function, parabola, at the point x equals 2. And our answer we got was 4 down here. Notice that there's no units after the 4, like there's no meters per second, just like we had last time. The reason for that is sometimes you're going to be asked to calculate the derivative of a function with no units. It's just you being asked to do a process without it being applicable to the real world. So obviously I prefer the problems that are asking you to apply it to the real world, but this right here is just for your algebraic practice, just like how do you do it, what are the steps kind of thing. So just notice like the answer is 4 here and no units are included after it. And then how do we get 4? So Rosa, the video is actually on today's assignment. It's due tonight. It actually walks you through the process and how we get 4. But basically after you do all this work, let me just exit this. After you do all these steps, to simplify our instantaneous rate of change expression, what you end up with is 2x. So after you simplify, you get 2x. And because they're asking you to find the derivative at x equals 2, you take 2 and you plug it in for x. So 2 times 2 is 4. But that's after you simplify this expression using a series of steps, which I explained in the video that I attached in tonight's homework. And you'll see. So you just have to watch the video and take notes and pay attention, but you'll see. Yeah. So the point of this slide, though, is to calculate the derivative is actually lengthy. It's big, right? And it makes you wonder, like, do we have to do this for every single calculus problem? The good news is no. For the assignment, yes, you're going to calculate their derivative with the formal definition because the AP exam does expect you to know how to calculate with the formal definition, right? But for other problems, it's okay to use shortcuts, and we're going to explore the shortcuts today. Okay, so let's first investigate what are the possible shortcuts. So what we have right here is a derivative table for the function f of x equals x squared. So this kind of correlates with the example I just shown you because this was the same problem, and at x equals 2, the derivative was 4. Right? And then this is a derivative table. It's doing it for all these x values. So at x equals -1, the derivative or the instantaneous rate of change is -2. At 0, it's 0. At 1, it's 2. 2, it's 4. 3, it's 6. So first, I want you to think about what do you notice? Do you find any pattern? Things like that. This is going to be our participation point. Let me know first off if anyone has questions about the derivative table. And just again, remember, derivative is instantaneous rate of change. That's the same thing. Okay, so if there's no questions about this table, I'm going to go ahead and have you all jot down your ideas in our participation Google Doc. Oh, okay. Oh, okay. Juan, make sure you save that thought right now for our participation doc. I see a juicy thought there. Where is our participation doc? Oh, I have to actually look for it. Give me a sec, y'all. I think it's because I'm sharing slides with another math teacher, so they perhaps took out my participation. There it is. They probably accidentally deleted my thing I did. There we go. Let me grab this. So right here, the question is, what patterns do you notice and what do you wonder about? So this is again open for those who can't see a pattern. You could go ahead and put down what you wonder. And then for those who are ready, go ahead and type in your name or initials and you're going to put down what you're wondering. Let me copy the link and let me put it in the chat. All right, everyone's going to do their own thoughts on this. Go ahead, let me clear my thing. Take about a minute or two. Make sure you write your name or initials for your participation. I will be entering this right after class. I definitely want to make sure y'all can get some in-class participation. So we have 9 that are on the document. We need, we have 10. We need 6 more people. Let's get on this document. All right, we have 12 that are on the document, and we need 4 more. Who are we missing? I'll just send you a little chat if you're having trouble on here to get on this document. All right, we need 2 more people to get on this document. Yay, we're just missing one person. If your name is up here, awesome. Let's shout out for those who are on the document already. Oh, we have anonymous tiger. Someone's just not logged into their Gmail. All right, let's see who we're missing. All right, everyone take some time to write down your thoughts on our participation doc. All right, cool. I sent you a message. If I'm missing your name there on the doc, definitely want everyone to go ahead and put your thoughts down there. Again, either your initials or your name. And then sorry for those who it's highlighted. It's because I in the past had highlighted some answers. I'm gonna give you all a few more seconds to finish up your thoughts, and then we'll take a look at what you'll notice. Okay, anonymous tiger, I know. All right. As y'all are finishing up, let me just go ahead and read through some of the things y'all are thinking about. So the derivative section increases by +2 for every x. In other words, the rate of change is 2. Increasing by 2. So in other words, the rate of change is 2. Yeah, because the derivative is the instantaneous rate of change there. I see they're going up by 2. Yep, that's a common one. In the x section, it increases by 1. Yeah, so in the x values, it's increasing by 1, but in the derivative, it's increasing by 2. I want to say it's the rate, but the derivative increases by 2. No, that's perfect. The x goes by 1, derivatives by 2. I think we're all noticing that. Let's see if there's anything different. I like how this one's specific, like it's in particular for this function, right? That pattern is happening. So every different function is going to have a different pattern. But if we try to figure out a pattern for this one, we could kind of generalize every other function so we can make it easier to find the derivative. Whatever exits, it's always doubles, even if it's negative. Yeah, I wonder if it's doubling on purpose. All right, y'all are noticing the same things. All right, so yes, the pattern is increasing by 2 each time. So if I was to write a function to represent the derivative, because it's increasing by 2 each time, this is how I'd write it. So I'm writing it right here. So maybe y'all can write it in your notes, but I'm going to put it right here. And let me change my color to black. So if I'm going to create a function to represent the derivative, I'm going to say f And remember, y'all, I introduced you to the new notation yesterday. I'm going to be using the prime notation right here. F prime of x, that means derivative. I'm creating a function to represent the derivative for this particular original function right here. So the derivative, because it's increasing by 2 each time, the function is going to be represented by 2x. And y'all can check that, because if you plug in these x values in for x, you're going to see that you get the derivative value. If I plug in -1 for x, I get -2. If I plug in 0 for x, I get 0. Plug in 1, I get 2. So what have we just done right now is, using a table, we've constructed the derivative function. And this derivative function will represent any instantaneous change for any x. We just got to plug in values for x, and it'll tell us the instantaneous rate of change at that specific point. So there's a pattern that we've just seen. And then let me check out the chat. Yeah, and Rosa, yeah, you were close, because you were making connections to y equals mx plus b. That slope, perfect. Those of you who mentioned about that was the rate or the slope, that's what is meant indeed. So what is the general pattern? So I want you all to take a look at what's going to be the pattern here. So I want you to notice that in order to get from here to the derivative function, basically, did y'all notice that this 2, the exponent, kind of came down? Let me go to the side. So in order to get the derivative, this 2 kind of went down, right? Because to get the 2x. And then what had happened was, like, this got subtracted by 1. In order to get a power of 1, because 2x to the first power is the same thing as 2x. So the power came down, then the exponent got subtracted by 1 to get the resultant function, which is the derivative. What I'm just right now describing is something we call the power rule, and it is the shortcut to find derivative functions. Right now, this was general. Don't worry, I have a slide where I talk about what is the power rule, but this was just for you to make that connection. Notice the power came down, then I subtracted 1, and you get your function. All right, let me go ahead and clear this. Again, make sure you put your name or initials for your credit. And let me go back to my slides, because I actually have this down. Yeah, so this is the power rule. So the thing I just described. So this you definitely want to write down. It is a shortcut. If you don't got the shortcut down, well, my friend, you're off to calculating the derivative the long way, which is like, it takes up like half a paper if you do it the long way. So here's the shortcut. Take the exponent and you multiply it by, so for example, in this scenario, this 5 came down. So 5 times 3 gave me 15. Then I had to subtract 1 to get 4. That's how we got the derivative here. So that's the rule. Bring the power down. You have to multiply it if there's a number already there, and then you subtract by 1. So that's an example, and we're going to do more examples, don't worry. But get this down, and I put a little note here that this power rule, the shortcut, works with functions that have integer powers. There's actually different rules for other functions, but this in general works with polynomials. Polynomials are functions that have like powers, integer powers, positive integer powers. Let me let y'all get this rule down. Let me keep this on for like 45 seconds. And then also any questions, feel free to ask. I could even do more examples if you're like, wait, what if you have this?
So could this be continuous? Okay, so we do like, is this, or I guess I'm saying, like, is this a one-time thing? Like, we do 3 times 5, and then like, could we do 15 times 4, or?
Oh, oof, yeah, that's a good question. Like, you're kind of saying like keep going.
Yeah.
No, yeah, you only stopped once. Later on in our calculus class, The thing you're describing would be called the second derivative if you were to do it again. So you stop after doing it once. That's correct. You don't keep going. This right here is the derivative. If you did it again, that would be called the second derivative, and that will represent something else. It won't represent an instantaneous rate of change.
So do these two still? But these wait. So do these two still represent the same thing or no?
Do these two still represent same thing? Like you mean f of x and f prime of x?
Yeah or no?
So this represents the original function, and this represents the derivative. And the derivative is the function that gives you the instantaneous rate of change at any point. Instead of doing that long, that long calculation to find the
Right.
derivative. Yeah, instead of that, that's what this part is. So down here is the derivative. And you could plug in any values for x to get the instantaneous rate of change at exactly that point. And remember, I know for y'all, derivative is a new word, so I'm trying my best to remember to say, which is the same thing as instantaneous rate of change. So that's just, this is the derivative, and this is the shortcut method instead of using that long formal definition, which you'll see in the homework that's due today. That's the long definition, and you're gonna kind of value, hey, I wish I could use the shortcut for this homework, but in the homework, you're being asked to use the long way. Then after that, we're gonna do shortcuts. Cool. Any other questions on that? These are good questions. All right. Let me go ahead and clear my board and let's do some more examples. Let's just get some more out there. Actually, the next thing I'm going to talk about is constants. This is important, so let's make sure we write this down in our notes. Okay, power rule. Okay, what do you do when you have constants added at the end, or just in general, what's the instantaneous rate of change or the derivative of a constant? And what I have for you right here is the graph of a constant function. It's a horizontal straight line, and I believe it's f of x equals 3. Oops. So here's the answer, everybody. So the derivative, aka instantaneous rate of change, of a constant function is actually always 0. That's because the graph is horizontal, and thus the slope at any point of the graph is 0, right? Because if you have a straight horizontal line, there is no rise over run. It's 0. So for example, this is my original function, f of x equals 3. It's right there represented in the graph. The derivative of this function is going to equal 0 because there is no rate of change happening. So my answer, the derivative of this function, is 0. Notice I'm using the new notation that represents derivative. That would be it for example 1. That's your answer. The instantaneous rate of change anywhere for a constant function is 0. So if this was a car, if this represented the motion of a car, the car isn't moving at all. It's just staying still. So therefore, it's instantaneous, or any rate of change is going to be 0. There's no motion. So that's how you would kind of relate this to the real world. But this is just in general for any function. I'll pause here to see if there's any questions, clarifications. And this is a rule. The derivative of any constant is 0. So that's a rule to memorize as well. Few more seconds. Make sure you get this down. All right, let's go on, y'all. So that's the derivative of a constant. So if I ask you, what's the derivative of f of x equals 100? You're going to say 0. The derivative of f of x equals 1,000, 0. The derivative of a constant is always 0, no matter what that constant is. The constant can also be negative. The derivative of f of x equals -1. going to be 0. So that's just a rule to remember. Now let's get to the actual juice of actually applying the power rule to a real function. This is example 2, everybody. Find the instantaneous rate of change for the function f of x equals 3x squared plus 5 at x equals 1. Now this right here is a type of function that you can use the formal definition to calculate it, but it might take you more work to do so. So for this problem, we're going to be using the shortcut. Notice how in example 2, I said find the instantaneous rate of change for the function. I could have said find the derivative. They would mean the same thing. They're synonymous, basically. I'll let you copy this down first. That way you can pay attention to the steps that I do. And then on the side here, notice I just copied and pasted the rule so you could take a look at that. Bring down the exponent, multiply it if there's a constant in the front, and make sure you subtract by 1. Also, keep in mind the derivative of a constant is always 0. Those are the things to keep in mind. All right, so here we go. Here's the derivative. So first, look at it, copy it down, so we can maybe ask some questions. So I want you to notice how I kind of like kept the 3 on the outside. I kind of didn't want to pay attention to it. I brought the exponent down. So 2 came down in the front right here. Then, according to the rule, I have to subtract the exponent by 1. So then I did 2 minus 1 to get 1 right here. Plus, I had to remember the derivative of a constant is 0. So that's where 0 came from. The derivative of a constant is 0. That comes from example 1. This one right here is power rule, the one in purple. And then I kind of just ignored 3 for the moment. Let me just pause and see if anyone has questions. So there's a question right here. If there's no coefficient, should we still decrease the exponent by 1? Yes. Yes. So if it was just x squared by itself, you would just bring down the 2 and then still subtract by 1. That's correct. I'll just pause here again for any additional questions. Again, remember, 5 became 0 because the derivative of a constant is always 0. Here, we're applying the power rule because we have an exponent. So we can use power rule. And then we have, someone said privately, would the answer be 6 for x equals -1? Sorry, for x equals 1, not -1. And that's something maybe to think about. All right. Let's go ahead and simplify if there's no question. So of course, x to the first power, that's just like x. We don't need to really write that. And plus 0 doesn't do anything, so I'm going to simplify it to this. Well, I should have already gotten rid of the first power thing. There we go. So yes, so after all that simplification, you should get the derivative. The general derivative function is 6x. But because we're trying to find the derivative at a specific location, right? Like a specific, let's say this is a car traveling and I want to know how fast is the car going at 1 second specifically. I'm going to take that 1 and I'm going to plug it in here. And that's going to give me the instantaneous rate of change at that point in time. Plug it in. And your answer is 6. Notice there's no units again because we don't actually have a real scenario here. This is just a general function that we're taking the derivative of. And yes, to that person who said in the private, is the answer 6? Yes. Notice how I didn't have to use the long definition to calculate this. I used the shortcut method. And verbally, how you would like say this, you would say this, the derivative, aka instantaneous rate of change, for this function at x equals 1 is 6. So there's our verbal interpretation at the bottom. All right, let me pause here for any questions and for also for y'all to get this down. Does that mean if we have a problem like x to the fifth, it'll turn into 5x to the fourth? Yes, that's correct, Sophia. Oops, sorry, y'all. Oh no, I didn't put animations to the other one. The problem. I forgot PEMDAS. That's okay. I think in general we didn't do PEMDAS at this spot. So this one's not PEMDAS. This is us applying this here new rule in AP Calc. All right, and it looks like when I tried to do it, so my timer went off. So I hope y'all got this down. So for the next one, give me a sec because I noticed I don't have my animations in for the next slide. Now where are we? We're right here. So I thought I did my animations. A paragraph. All right. There we go. So let's go back to the original problem. Remember, so we actually first started by talking about how the secant becomes a tangent line with this problem. It was the ball being thrown. And we're trying to find how fast was the ball moving at exactly 2 seconds. Let's use what we just learned, this power rule, to figure out the answer now. So this is going to be example 3. Remember, the goal was we were trying to find the instantaneous rate of change at x equals 2. And what we were doing was some old school approximation methods, which is not bad, to be honest. Approximation is good, but it's not going to get you the perfect answer. So previously, though, I didn't tell you the function. I just gave you the Desmo screenshot, but here's the function. You do need the function if you want to use the power rule. So the function that represents the original curve we're looking at was f of x equals negative 5x squared plus 12x plus 2. So remember where we left off. In example 3 from the last class, we said that the closest instantaneous rate of change was negative 7.9 meters per second. Let's see what the exact instantaneous rate of change is using the shortcut to finding the derivative. Let's see. Let's remember the rule, because I don't have the rule here on this page, but remember, bring the power down, subtract by 1. Here's my derivative, everyone. Take a look at how I set that up. For the x squared, notice I brought down the 2, subtracted 1. I even did it to the x, because there's an imaginary 1 right here. So I brought down that imaginary 1, and then 1 minus 1 is 0. Notice how that happened there with that x. Just pay attention to that one. And then again, because we have plus 2 at the end, the derivative of a constant that's by itself is always going to be 0. So let me let you all process that and maybe come up with any questions, but just notice how the derivatives are showing up here. So let me just draw some lines. All right, I think I see 2 things in the chat. I wanted to multiply 2 by 1 first. I was confused. Oh, sorry, Rosa. Was that to the previous one? Or was that to this one? And then I have a private chat. Is it 4? I'm not sure, to be honest. I haven't yet worked on this problem yet. I'm not sure if it's 4. We actually have to walk through it and see what the answer is. So far, this is just the first step. I use the power rule to take the derivative first, and then we're going to simplify it. All right. Let me know if anyone has any questions about the parts, the blue lines, you know, like what did I just do right now? If no, let's go on to simplify the derivative. So this is what we get next. 2, so negative 5 times 2 is negative 10. X to the first power, well, that's just x. Now over here, so right here, x to the 0 power, you have to remember anything to the 0 power is 1. So this became 12 times 1. So that's super important. Anything to the 0 power is 1. The plus 0 disappeared. We don't need to add in plus 0. That doesn't really affect our answer. So pay attention to anything to the 0 power became 1. That's super important. I know there's a typo. I can't fix it no more. I mean, unless I retype it. Anything to the 0 power is 1. That comes from right here. And this part simplified to this. Cool. Let me know if there's any questions. So someone says, so I think the final answer would be -8, I think. Well, let's see. All right, let's go ahead and further simplify this. So we have -10x plus 12 times 1. Well, 12 times 1 is just 12, so I'm going to rewrite that. All right, so now that I've simplified the derivative as best that I could, now we could go ahead and figure out what the instantaneous rate of change is by plugging in the point of interest. So we're going to plug in 2 into our derivative function. Once we do that, we're going to get the exact instantaneous rate of change at x equals 2. That was that problem we were doing the other day in approximating. I get this, plug in 2, multiply, you get -20 plus 12, which is equal to 8. Sorry, -8. Give me a sec. You're right. Because the slope was negative. It has to be negative. Sorry, y'all. Present. Sorry. Re-put everything. I don't want to mess that up. Okay, there we go. -20 plus 12 is -8. Because this problem originally did have units, the ball was going at -8 meters per second at x equals 2 seconds. So that was at exact speed at x equals 2 seconds. So this is the interpretation. The derivative or instantaneous rate of change at x equals 2 seconds for this ball's motion is -8 meters per second. Sorry, let me check the chat. Yeah, you want to put the 2 back in. That's correct. Once you simplify the derivative, you plug the 2 in, and then you get your instantaneous rate of change. All right, and then Sophia has a great clarifying question about the derivative rule, the power rule. So if we had -5x to the third, it would become, bring down the 3, -5 times 3 is -15, x squared. Yes, that's correct. I love those clarifying questions. Because then everyone, maybe other people are thinking the same thing. All right, so let's see if we have time for one more, and then we'll jump into our exit ticket. So let's see if we have time for one more example. Maybe some of you got the steps. If not, that's okay. Don't worry, because you know, you'll have some practice on that. We'll make sure you get some practice. And or jump into office hours. I haven't seen any AP students yet. Office hours, just a lot of pre-calc, but jump on in. It's Monday through Wednesday at 10. I'm happy to also support. Also make up any work. I'm happy for that too. Guarantee to give you all full credit if you make up stuff, but you don't want stuff to pile up. That's why I keep bothering about getting your stuff in. All right, y'all. So that was our answer. Notice how we did this with the shortcut method instead of doing that approximation, which was lengthy, right? We did that the other class time, and that took a while. And if you did the formal definition of the derivative, it took you a while too. This is the fastest way to get the instantaneous rate of change. And this is exactly, because we're using limits. This is not an approximation now. This is the instantaneous rate of change. -8 meters per second was the ball's speed at x equals 2 seconds. All right. Now what's this? Oh, okay. So this is another one, just so y'all can get further examples, and then we'll do our exit ticket. And that's gonna be the last thing before we, yeah. Let's do one more. This one I tried to include like a longer polynomial so we could put this practice. I also want you to notice in this problem, it doesn't say at x equals. This is generally asking you to just find the derivative. That means we're not asking for an actual point. We just want the derivative function. That's it. So just pay attention to the difference there in the wording. All right, maybe some of you are already getting started on applying the power rule. Remember, bring down your exponents, subtract by 1. This is what it should look like, y'all. Take a look. 5 came down, subtract 1 to get 4. 4 came down, subtract 1, you get 3. So forth, take a look at that. And again, notice how I also applied it right here because we have an imaginary 1 as an exponent. And minus 1 became minus 0 because the derivative of a constant is 0. So just pay attention to what's happening. Make some sense of it right now as you're taking a look at the steps. Then after this, to be honest, all you got to do is simplify and then you're done because we don't have to plug in a point. This is just saying find the derivative. Mm-hmm. Okay, so things to remember when you simplify, you're going to multiply any constants that are in the front if they have an x after it. X to the 0 power is always 1, so this is going to become 2 times 1. Minus 0 is going to disappear. Minus 0 doesn't do anything, so this is what we get when we simplify. And our last final thing is we just got to do 2 times 1, and that's our derivative. That's our answer. That's it. Notice this one, we just want the derivative function. We're not asking at x equals something. This is just the general derivative function. And then Viviana says, can't you just use the derivative in the beginning? You can, yeah. Like for me, it's like I'm just spelling out the steps for the students that need it. If you can already look at this and write the derivative, like go from the first thing to the end, that's awesome. That means you got this down like that. For me, I'm just making sure I show it step by step for those students who need that walkthrough. But definitely, Viviana, you could totally do that. That means you got this, so that's cool. That's what I do, just so you know. Like I just, yeah. All right, that's it for this one. That's example 4. Let me know if anyone has any last minute questions before you all get your exit ticket. And yes, make sure you submit this exit ticket. Some of you haven't, like maybe there's like 3 or 2 of you that still need the last one too. These are graded, so you want to make sure you're submitting your exit tickets. It's not based on accuracy, it's just based on your attempt. I just want to hear your thoughts. It's okay if you're confused, Rosa, but I'd like to see you in my office hours for sure if you're confused, because I'd like to work on you one-on-one so we could get this down. And then just put where specifically you're confused on in the exit ticket so I could follow up with you. Yeah, for sure. All right, let's get on to the exit ticket, y'all. Yay, exit ticket. Oh, by the way, here's the interpretation of this one. I forgot. This is for any x value. You can plug in any x value for x, and the derivative would give you the instantaneous rate of change at that specific point in time. See how useful this is? It's like you don't have to keep doing the calculation for different x values. This one, you plug in any x, and it'll tell you the instantaneous rate of change. So that's how useful this is. All right, so let's go on to the exit ticket, y'all. Let me give this to you. Make sure you complete it. Make sure you submit it. And then those of you can go ahead and get started on the exit ticket. And Rosa, what numbers are you talking about? Sorry, clarify. And feel free to unmute or you could type. Go ahead and get started on the exit ticket.
We were getting the 5, like for example, like 5x
Here?
to the root of 4.
Yes, that comes from, let me go back.
Yeah, you got it from 5. You put the 5 next to the x,
Yes.
and then you put minus 1 because you put it next to the x.
That's correct. It comes from the power rule.
Now I got it because I was confused. I'm like, hold up, where'd she get that number from? Yeah, thank you.
Yes, always. Perfect. You're welcome. All right, y'all, get to that exit ticket. Now, we are at the end of class, so please feel free to just get this done. But please make sure you hit enter. If not, I could send you an email, but I definitely want you to get this down. Again, there's no way you can get this wrong. You just want to participate on the exit ticket. All right, everybody. Y'all have a great lunch. I'm gonna go ahead and end this class. And yeah, we're gonna have a week off, everybody. So enjoy your break. And yeah, bye, everybody. Get that exit ticket in, though. Bye. Or feel free to stay if y'all have questions. I'm happy to help.
Mr.
Bye.
Donner,
Yeah.
are you gonna post another async tomorrow, or is it just the one for tonight and that's it?
Yeah, I wish. Yeah. There is one more, and that's due Sunday. And then that will be it. So it's going to be practice on the power rule.
All right. Cool. Okay, cool.
Thank you for asking. All right. Bye. Bye, Edgar. Bye, Sophia.
I wanted to ask. Okay, because like I'm confused of what exactly is the. Like I was looking over my notes, but I'm kind of confused on exactly what the difference is between the derivative of f the derivative and like the normal f of x.
And the normal f of x. So the normal f of x, think of that like, you know, in physics, if you have a distance time graph, that's your normal f of x. Just like a car traveling, or a position graph, like a car traveling, or you're walking, right? You have like distance and time.
Right.
The derivative function would represent the velocity, like a graphed function velocity, like how fast you're going over time. So that's what they would represent if you're talking about the real world. So f of x represents like distance, if you think of it, and then the derivative represents velocity.
And the derivative, that only applies to does that only apply to the tangent line?
The derivative is the slope of the tangent line, yes.
But not the secant line.
The secant line helps you approximate the tangent, but the secant line will never become the tangent. So like even as best as you could, if you did use the secant line, the best approximation you would get would be like, you know, for that problem, the -8 meters per second, you would get like -7.9999. It would never arrive to 8. And the derivative will give you the perfect answer, the actual instantaneous rate of change.
Okay. I get them. All right.
Awesome. Yeah. Thank you for the questions.
Thank you.
You're welcome.
All right. Have a great break.
You too. I'll see you if I don't see you later. Or I'll see you tomorrow too. Tomorrow we're going to have a Panthers of the Month celebration for advisory. I don't know everyone's Panther yet, but yeah. All right.
All right. Have
Bye.
a good break.
You too. Bye.
Bye.
Bye. And then Evie, let me know if you need any help or anything or any support. I'm here. I'm going to go ahead and end the meeting though in case you need anything. Bye.